Hello, on this occasion I want to present the results of the research of this paper. We present a mod called SAMBot that consists of a quadcopter protected with a spherical case and a manipulator attached to its front. This design combines the advantage of the protected drone to access complex spaces such as orchards and the ability to maneuver and access in small spaces of the manipulator. The rest of the explanation is shown in the paper, but as I said at the beginning, the objective of this experiment is to observe the behavior of the proposed design using classic PID control methods. You can see the PID parameters that we found in this part of the graphical user interface that we have developed to modify these parameters in real time. From this other panel, we can send flight commands to the drone, as you will see below. On the other hand, the joint trajectory controller of the ROS2 control package has been implemented to control the manipulator. We send commands from this UI that we have developed. Now let's look at the flight command sequence that we will send to prove our system. Okay, so now we are going to send a command sequence to describe the movement of the system. First, we are going to move previously the manipulator to a home place. We send that signal and you can see that the manipulator moves. So now I want to send a hovering movement. That means that we are going to send meters in the z-axis, and as you can see, this action affected the x and the z-axis. In both cases, mainly for the x-axis, it was more difficult to reach the reference. However, as you can see, the system did not present oscillations that affect its stability. So now we are going to stretch the manipulator and now it goes backward and almost reaches the reference that we want. And this is because the PID parameters were primarily tuned for this case. So the error is nearly zero. Now we're going to retract the manipulator and you can see the perturbance again in the system. But this time I want to move in the y-axis 1 meter. As you can see here, it reaches the reference rapidly. So we want to move again 2 meters in the right sense. That means that I want to put -1 meter because it going to move 2 meters. Okay, we send that signal and we can see that it reaches rapidly again. Okay, now I want to send a forward command of, for example, 1.3 meters to the front. We send that signals and you can see here that is a little overshoot and then almost reach the reference. Again, we are going to send to the 0 position all that, and then we send that command. As you can see, it's a combined movement, and it reaches rapidly again the position. Then we are going to send a yaw movement of 1.57 radians, and this time it reaches slowly the reference. As you can see, the graph shows that the yaw error tends practically to 0 in stationary state. So then we are going to send 0 because I want to move again to the home position, and it reaches almost at the same time in the opposite sense. Okay, now we are going to send that signal because I want to land, but after I want to be near to the ground, and then send the land position because I want to finish this experiment. Well, as I mentioned before, the objective of this experiment is to prove that our design has the right characteristics to be controlled with a classic PID with a certain degree of stability. Our next step is to implement a more sophisticated controller, whether adaptive, robust, or a hybrid that uses artificial intelligence with visual feedback through the camera mounted on the manipulator and its built-in distance sensor, so that it reaches the desired reference in less time and reducing as much as possible the overshoot that appears in some of the graphs. And well, that's all for now. Thank you very much.